Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor James Kakalios, who is Professor, School of Physics and Astronomy at the University of Minnesota. His current research ranges from the Nano to the Neuro, with active studies of the optical and electronic properties of materials, to investigations of voltage fluctuations in the brain. Welcome, Jim.
Thank you very much for having me, Gil. Pleasure to be here.
Oh, yeah, thanks for doing this. So I want to start with one of your earlier papers entitled Transient Striatal Gamma Local Field Potentials, Signal Movement Initiation in rats. Transient coherent neural oscillations, as indicated by local field potentials, are thought to underlie key perceptual and cognitive events. So you have a rat experiment here, and so these rats are running, and you're picking up signals from their brain. So what is the experimental setup here?
Yes, that title just rolls off the tongue, doesn't it? Well, I'm in physics, and I'm a humble but lovable condensed matter physicist. So most of my research, my background, my training is in solid state physics, in semiconductor physics. And when I got to Minnesota as an assistant professor, we were doing measurements where we were measuring electrical noise in amorphous semiconductors, disordered semiconductors. And long story short, well, first of all, we were doing that because not all noise is created equal. And as physicists, we believe that everything has a reason, even random fluctuations. Sometimes the random fluctuations are coming about just because the sample's at some temperature and the atoms are vibrating and there's nothing more to be learned about it. And sometimes you see fluctuations in the current that tell you that there's some other reason, some deeper mechanism at play. And so looking at the noise in amorphous silicon, we concluded that the noise was coming about from inhomogeneous current filaments, so that the current wasn't going in uniform between two electrodes, but was taking like serpentine, little snaky pathways because of all the disorder in the material. And moreover, that these filaments were changing in time because of atomic rearrangements that were happening at room temperature and at warmer temperatures. So basically, you had like a mountain range, and it was flooded, so the water was flowing through little valleys. But since there was plate tectonics that was going on, what was a valley becomes a hill. What was a mountaintop becomes a valley. And so we were seeing changes in these filaments with time. And I thought, hey, I know another system where there are current filaments who are inhomogeneous, that vary, that change with time, that fluctuations in one filament are related to another filament. The current filaments in your brain. We have ions that are flowing from neuron to neuron, and they take snaky little pathways, and they change. They change with time, and one thing leads to another. And
that you're talking in the thin film. The noise is that the electrons are not following sort of a straight line.
So what happens is you have like two metal electrodes, and maybe they're like a millimeter long.
Yeah.
And the gap between them is, say, like a millimeter or so. And you apply a voltage to one electrode, and you draw a current through the material, and you pull it out through the other electrode. Even though the voltage is dropped all across that 1 millimeter electrode, there could be variations in the resistance in the material down at the nanoscale level, such that the paths of least resistance are not just like uniform across the material, but there are little, like, little percolation type paths, little, as I say, microchannels, some sort of inhomogeneous filaments, because of disorder down at the nanometer scale. And so the electrons are taking actually a kind of a very serpentine filamentary path.
So is the power going from so there is a gap between the two, and it's essentially electrons are jumping from one to the other?
Well, it's not so much that they're jumping; they're flowing. Yeah. You have a semiconductor that has a resistance.
Yeah.
And you measure its average resistance, and you say, oh, so it has a resistance of, say, 1,000,000 ohms, whatever it is.
Yeah.
10 million ohms. And you apply a voltage and you get a current. That's great. Yeah. But down at the atomic level, the current that's flowing is actually flowing through, like, there are regions where there's actually much higher resistance than average, and much lower resistance than average. And so it's flowing through the current. Of course, the electrons like to move through regions of lower resistance. So it's taking these other pathways. And these pathways are not straight lines connecting one end of the material to the other. They take loop-de-loops, and they take all sorts of circuitous pathways. And moreover, because of atomic changes that are going on, what was a low resistance region may become a higher resistance region, and a region that was kind of blocked suddenly can be connected up, and now it can carry some current. And so we would see variations and fluctuations in time of the current. And this leads to, so if you look at the fluctuations of the current, not the average current, but how it's fluctuating, it was fluctuating in a non-trivial way, which is, a physics talk for saying we don't understand it. But it was fluctuating in a way that revealed information about what was going on at the atomic scale. And
okay, so we call it noise.
So we call it noise. Yes.
Yeah, the fluctuations. So that slight differences in resistance and the current that you're measuring, the micro fluctuations that you see there,
yes,
is what you're calling noise. And now, so how is that related to the rat experiment?
Great. That's exactly where I was going next. So what happens in the rat is when we look at this noise, this electrical noise in the semiconductor, we're able to actually, by doing various statistical tests, we were able to extract information about the filaments, whether they were turning on and off, whether one filament turning on, did that affect another filament and make it turn on or off? And so we could get information about the nature of these filaments by looking at the noise. So I thought, hey, I know that there are current channels in the brain, and they are not stationary. They're not permanent. They're constantly evolving and changing. You're having different thoughts. And so I talked to some neuroscientists who usually, when I I described these ideas to them. They kind of smile and then call for security. And then I met this guy, met this professor, David Reddish, who said, you know, I described about how I thought that the changes in the statistical nature of this noise would reflect changes in memory. And he said, I'll never forget, it was a great moment. He said, well, these ideas you have about how memory works are completely wrong, but this noise stuff sounds pretty interesting. And so it led to a collaboration. He was doing the experiments on the rats, and we would help, my graduate student and I would delve into it to try to get information out of this. And so the thing that we learned, and I you know, the brain is obviously so complicated and so difficult that there's no one approach that to understand what's going on. So you have people who have backgrounds in biology and chemistry, you have electrical engineers, you have physicists, you have mathematicians, you have neuroscientists even, who are all working on this problem, and they all come at it with their own expertise, and sometimes, you know, thinking about things like a physicist and thinking about things like a neuroscientist, it kind of clicks together. What we saw, it turned out from these studies that the noise itself was not that edifying. It was actually, the noise itself was too complicated for the techniques that I was talking about to apply. But what the techniques turned out to be very useful for is finding there were signals that were buried in the noise, and our techniques were able to find these signals. So when I say signals, what do I mean? You stick an electrode into a rat's brain, and I don't advise you to just do this. You should leave this to the professionals. But when he does an experiment, they have these rats, they perform surgery, they insert these electrodes into their brains. They're awake, they're alive, they're performing, but they have these, you know, electrodes in their head that can be then monitored, and they can record the voltages from different portions of the brain. You may have heard about people talking about the brain, and they talk about alpha waves or beta waves or, you know, theta waves or things like that. I had heard about this, and I never really gave much thought to what they were talking about. But it turns out that it's not like there are these continuous waves, sine waves, that are going on in your brain, like, you know, a pendulum constantly swinging back and forth, back and forth. What happens is, in these you look at the voltages that you're recording on these electrodes that are in the rat's brain, and you see things that are just totally random, fluctuating voltages. And then suddenly, many electrodes all at the same time will all click in and record something that looks like a sine wave. And it will last, maybe it lasts 100 milliseconds, maybe it lasts 10 seconds. And then it just as suddenly as it appears, it goes away. That's called a coherent oscillation. Most neuroscientists would bet you cash money that it's very significant, and they would also admit that they have no idea what it means. It's like, it is this remarkable sine wave, and different parts of the brain have different sine waves, and they have different frequencies. And so some frequencies are called the alpha, some are called the beta, some are called the gamma, and that's what alpha waves, beta waves. So they stick in these electrodes, and you suddenly see an oscillation that suddenly pops up and then disappears. And
so you see sort of what you might expect in a physical system for a brief period of time.
Yes. So here would be the analog in a brief physical system. You have 100 metronomes, like you use a metronome for your piano, right? And you have 100 metronomes, and they all have like the standard frequent, you know, tick, 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 right? But they all got started at 100 different times. So all you're hearing is a background noise, because some are clicking, some are off, others are clicking, some are ticking, some are talking, And so they're all going on at, completely at random, and you're just hearing background noise.
Yeah.
And then suddenly, for reasons unknown, not well understood at this moment, suddenly they all start going tick, 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 all together. And then
Is it similar to resonance, Jim?
it could be.
Yeah.
But resonance with what? And it's a
Yes.
dynamical resonance. It's something that's not like structurally there. It has to do with, and it has to do with them talking to each other. The resonance doesn't extend, it's localized because it's, one part of the brain, it doesn't make the entire brain go into sync. It's actually even not so much, it's not clear that it's a resonance. It's like you're at a party and 100 people are talking and all you hear is the background white noise of 100 different conversations or 50 different conversations. And then suddenly, with no warning, kind of like a flash mob, they all start singing the same song in phase, at the same time. And then they stop and they go back to having their conversations. And so what the problem is, you don't know, if you go into a new portion of the brain, you don't know what frequencies you should be looking for. They could be very long frequencies. They could be very short frequencies. You don't know how long they're going to last. They could last, as I say, tens, hundreds of milliseconds. They could last many seconds. So you're trying to sift for gold, but you don't know how big the gold that you're looking for is. So you don't know what size grid you should have in your screen, you should have in your pan. Should you have a fine mesh or should you be looking for boulders? You don't really know. So what we did, what our physics contribution, and it's, too mathematical to go into, but basically we said these two simple commands that you can give on a computer program in MATLAB automatically would tell you what frequencies to look for. That it looked for whether there was any frequency that was talking to neighboring frequencies, and if that was the case, it flagged that as an important frequency, and that way, otherwise, you have 40 minutes of data. And if you're looking for little stretches of 100 milliseconds each that are appearing at random and you don't know what's going on and you don't even know what frequency to look at, your only hope is to take each data point and like break it 40 minutes, break it into 1 second intervals and squint at the data. And then you go to the next second and the next second. And that's what people were doing, was basically, there was a fancier term, but they were squinting. And so this technique took the squinting out of it. It said, okay, you have this 40 minutes worth of data and you run it through this program, and it said, these are the frequencies you're looking for. And it's like, really? And we did that for portions of the brain where people had found the frequencies through squinting, and our technique gave it to you right away. And then we applied it to a part of the brain that people hadn't well studied before, and it popped up and it said, there's a frequency that's right around 50 hertz, 50 cycles per second, and it's very tight. It's, it's not 60, and it's right around 50. And that's called the in general, it's called like the gamma band, for whatever. That's what they labeled it. Good. So we called it gamma 50 because it was a really tight signal. And this was in the portion of the brain that for rats controls voluntary motor control. So when you get up and start walking, or if you start riding a bicycle, you use one part of your brain. And then once you're riding your bicycle and you're just pedaling and you're looking around and you're talking to someone, maybe on your headphones or something, listening to a podcast, the fact that you keep pedaling and keep riding your bicycle, you're using a different part of the brain. And then when you have to stop or you have to change direction or do something else, the other part of your brain kicks in. So you have different parts of your brain controlling different aspects of doing something like riding a bicycle. It's not just one part. I'll tell you one thing. I didn't know anything about the brain before we started this, and I've done a little bit of reading and a little bit of learning on it, and I've come to one conclusion about the brain. It'll never work. I don't know who came up with this, but it is the most kludgy thing I've ever seen. So anyway, the
Yeah.
yeah,
So you have a way to extract data, in this case, from the rat brain.
yes,
And there is a lot of data, so you can actually process that data in such a way that you can find the frequency of oscillations in that data.
yes,
And, if I understand this correctly, Jim, in the particular experiment, you could actually predict what could happen, right?
Well, so okay, not so much predict, but we could find a strong. So yes. So what we did is, so now we found this signal in the part of the brain that controls voluntary motor control. That's rated around 50 hertz. So now that we know we're looking for a signal for 50 hertz, now we know what size, panning for gold, what size, grid we should use. So now we can filter the data and say, when did this 50 hertz cycle appear? We have 40 minutes worth of data. The rat's running a maze, get some rat chow. If he wants some more rat chow, he's got to run the maze again. If he successfully does it, he gets some more rat chow as a reward, and he keeps running the maze, and he gets his rat chow, he eats his rat chow, and it's completely up to him when he starts or stops. That's up to the rat. Now we can ask, what was the rat doing whenever this 50 hertz signal came up? And that was the really fascinating part. We didn't see it when he was running the maze. We didn't see it when he got his rat chow. We didn't see it when he was eating his rat chow or grooming himself. Every time the rat started running the maze, we saw that signal. So it was strongly correlated with the rat starting to run the maze. And that was more mind-blowing.
Yeah. To run the race, so starting to run the maze, so to speak. So the rat is making some sort of a decision. It's sort of starting to do something.
Correct. So I mean, you're looking at the rat, and basically what we did was we plotted the rat's speed as a function of time, and we said, where do we set the origin for our time axis? We'll say every time the rat, we see this, we'll say that's the start of the clock, and then the speed just like immediately takes off from there. So we can see, so it was his acceleration more than the velocity that we were triggering off of.
Yeah, it's a fascinating thing, Jim. So you're finding correlations, but we can't really say anything about the causation.
Oh, absolutely. No, and in fact, we had, when we first submitted this paper for publication, one of the referees raised a very valid objection. He says, you have this electrode that's in this portion of the brain, but you're also, there's like two other regions of the brain that are on either side of it. And how do you know that the signal you're measuring isn't a signal that's starting in region A and is going to region B, and you happen to be at region C right in the middle, but you're not seeing the signal originating where you think it is, but you're seeing it pass you by, and it was a great idea, and we had basically multiple electrodes, and we could look to see if there was any timing difference between when the signal was recorded. And we could move the electrodes up and down and back and forth, and we can see if there was any variation. And it turned out to be not a variation. But you're absolutely right. It is so hard to prove that you're seeing what you think you're seeing when you have a hunk of silicon that just sits there on the copper block and doesn't move and doesn't do anything. And when you're dealing with something as complicated as a brain of an awake, a behaving animal, to be able to prove, I mean, we found a correlation, and you could make a claim that that's all we found. Now, finding a correlation like this, I think is not nothing. It's not chopped liver, but it's
Yeah,
a correlation. And so the next step is to try to figure out what's going on. That's absolutely right.
yeah, it's a very interesting thing, Jim. So one of the things that I was thinking about is, there are experiments like this that is looking into, this question of free will,
Yes.
right? And there were some experiments that shows that the brain activity starts a lot before a physical
Right.
movement of an individual. In this case, it's a rat, um, and so there may be some implications here too, right? What you're finding is that this oscillation happens uh, either simultaneously with the rat accelerating, or perhaps there is a little bit of a lag before that acceleration and the signal might, which might be very interesting to study.
Absolutely. Absolutely. I remember being really thrown by those studies you talked about in terms of you see the arm move before the portion of the brain sends the signal that says move the arm. Right? Which is like, that is spooky action at a distance, let me tell you. I think that is actually understood, but it's not my field, so I can't remember. But I thought I read something where they found that there was actually, you were not seeing the muscle move before the order to move the muscle was going. There was something else that was going on. But you're absolutely right. In terms of, I asked the neuroscientists involved, what happens if we can prove that this signal is the rat actually deciding, I want to start running, right? What if that is the thought or something? And, he said, well, if nothing else, it's going to have huge applications for Parkinson's, right? Because Parkinson's, you know someone who has a Parkinson's and you think about them, you think about the shaking and you think about the wavering. But a lot of that is a side effect of the medications that they're taking, because Parkinson's is also the inability to control, to start or stop moving. And there are movies of Parkinson's patients that are walking down a hallway, down like a checkerboard pattern on the floorway, and they're taking their steps one square, one square, one square, moving on, and they're walking the same as you and I would be walking. But the problem is that they can't start it or they can't stop it. Once they're moving, the portion of the brain that controls continued motion, that works fine. The portion of the brain that controls starting or stopping motion, that's the one that's having difficulty. So
so experiment, Jim, did you get any data when the rat decides to stop from a running position?
I don't recall that we actually ever saw that. So but it's tricky. And this was not my main thing. I work with David Reddish. I had another student who then collaborated with the professor Tay Netoff in the biomedical engineering at Minnesota, who worked with him looking also at these coherent oscillations in epilepsy. And but then I went back to my nanocrystals. I'm looking at these nanocrystals now. We're putting nanocrystals in disordered semiconductors, like little chocolate chips, and we're finding that we can get materials that have properties that don't look like the nanocrystals. They don't look like the amorphous film, but they look like something completely between the two. And so we're playing around with that as well.
So we'll take a quick break, Jim, and when we come back, we'll talk about all those material stuff that
Very
we're
good.
doing.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we are back. Jim, we were talking about using some interesting materials in biological system experiments, especially in rats that we talked about in the previous session. But your day job is really about materials, isn't it? So there's a paper entitled Structural and Electromagnetic Properties of Dual Plasma Co-Deposited Mixed Phase Amorphous Nanocrystalline Thin Film. So before we get into the details of this, Jim, so what exactly is a thin film? And where do we see this in practical?
Sure. Okay. So when we say thin film, we're talking about like a thin coating on something that might be no thicker than a micron. A micron is 1/10,000th of a centimeter, and it's basically the size of like one of the cells in your body. And so this is a thin film that it's really thin because it's, as I say, it's no more than cell the size of a cell, or maybe a couple of cells.
Yeah.
You have they still have, you know, a tremendous amount of atoms in them. So they're still, you know, they're not like single atom films or anything sexy like that. But why are we interested? Why do we care? So think about silicon. The way we make crystalline silicon for the chips that are in your computer and your smartphone and in everything else is you have a big pot at very high temperature of molten silicon, and you put in a small amount of crystal and you pull it out very slowly, and the whole thing starts cooling as you pull it out, and you get a large big cylinder of single crystal silicon. If you do this very slowly, very carefully, and it's like a large, it may be a diameter of like, say, 12 inches, 14 inches. It's a giant baloney of perfect single crystal silicon. You have to do all sorts of materials processing to it to get the to get rid of defects and everything, but you can do that. And then you take this large.
Yeah, just a quick one, Jim. So these are not what's called sort of a two-dimensional material.
No. So those materials truly are like, you know, one atom thick. When I talk about it, so right now I'm talking about a large, you know, salami of crystalline silicon. You take it to the deli counter. They slice it into they slice it off into, you know, slices of salami. They're actually, you know, 12-inch wafers of crystalline silicon. You do all sorts of process stuff to this crystalline silicon, and then you are able to punch out, you know, hundreds of little microchips out of this crystalline silicon, and that's great. And those microchips, the silicon in them is like just beautiful, and it has wonderful properties, and it's the microprocessor, it's the memories, it's everything that's inside your computer right now.
Right.
Now, after I got my PhD, I worked for a few years at Xerox in Palo Alto, California.
Yeah.
Xerox frequently deals with things that are 8.5 inches by 11 inches, right? The size of a sheet of paper. At the time that I went there, they couldn't make 12-inch wafers of crystalline silicon. They could only make 3-inch wafers of crystalline silicon, maybe on a good day 4 inches. So how are you going to make a Xerox copy of an 8.5 by 11-inch sheet of paper if the semiconductor thing you have is no bigger than 3 or 4 inches? So what you do is you say, are you married to the fact that it's a perfect crystal? Can you get away from that? And so if instead of having every atom be in a perfect crystalline arrangement, like it is in the semiconductor chips that are in your computer, your microprocessor, and so on and so forth.
Yeah.
If you spray paint the atoms down at random, then it's very easy to coat 8.5 inches by 11 inches. It's actually very easy to coat like your entire tabletop. You could coat an 80-inch diagonal rectangle. And I picked that number for a reason, and I'll tell you in a second. Is that you could coat that if you're willing to just spray paint the atoms down completely randomly.
Right.
Okay, so that type of silicon where the atoms are not in a crystalline arrangement, but they happen to be just going down where they stick, that's called amorphous silicon.
Yeah.
And amorphous silicon is interesting for two reasons: science and technology. So let me talk about the technology first.
Yeah.
Xerox deals with sheets of paper, and you could easily coat your semiconductor that would scan the sheet of paper, and you could make it big enough to scan the entire sheet if the semiconductor is amorphous. You spray paint them down randomly. For solar cells, you don't want a salami of semiconductor. You want a large flat area. So that way you could soak up as possible. You don't want that salami and then having to put the little discs, the wafers, over. You want to be able to coat inches.
Right.
80 inches. You're right now, I'm willing to bet, looking at your computer monitor, and your computer monitor has an LCD screen, liquid crystal display screen, right? Your flat panel TV is a liquid crystal display TV.
Right.
We call these liquid crystal displays, but I call them amorphous silicon displays because behind each pixel is a little transistor. And that transistor gets a signal and it sends a voltage and it changes the optical properties of the liquid crystal and makes it either light or dark or changes the color. And so that's how you get the image on your TV and on your computer monitor. And we're Americans. We don't want 12-inch TVs. We want 80-inch TVs. And so you could not get an 80-inch crystalline silicon that covered an 80-inch rectangle, diagonal, 80-inch diagonal rectangle of single crystal silicon at any cost. Forget about how expensive it would be. You couldn't get it at any cost. But if you're willing to spray paint the atoms down randomly, it's dead easy. So
the manufacturing process then, Jim, so what you call
so the co-deposition was basically, we take the technique that is used to spray paint down the atoms randomly. And then we had another deposition system where we took the same gases, but we did other stuff to it so that we could make, instead of making just a thin film, a coating of amorphous silicon, we could make nanocrystals of the same material or of a different material. And then we inject the nanocrystals into, when we're spray painting down the amorphous semiconductor, and the nanocrystals get embedded in the material like little chocolate chips. And so you have a material, and we could do various tricks where we could change how many nanocrystals we have. We could change how big they are. Are they close together? Are they far apart? We could do all sorts of little tricks like that. And then we look at the properties of the material that we're looking at, and we see, are they sensitive to the nanocrystals? Does it change? Does it get better? Does it get worse? To our surprise, we found that when we put only about 2 to 4% crystalline material in there, it became a much better conductor of electricity. The resistance in the material dropped by a factor of nearly 100.
You can almost custom print.
Yes.
A product.
Yes. I mean, that's what we're kind of going for. We can make these amorphous semiconductors. We can make them for solar cells. We make them for our flat panel TVs. But there's many applications where we would like them to be just a bit better. Really, and that's where we say thin film. When you take that crystalline silicon salami and you take it to the deli counter and you slice it up into a wafer of crystalline silicon, that wafer is maybe 200 microns thick, right? Again, a micron is the size of a cell. So it's pretty thin.
Yeah.
But you're using this for a solar cell, and all the sunlight is getting absorbed in the first micron. So that means I have 199 microns of very high quality, expensive, and useless material that I still have to pull the electrical charges through to get my solar cell to work. That makes the cost of it higher. But if I'm spray painting the atoms down randomly, I can stop spray painting once I get a micron. And they say, well, done, good. And now, so that's the thin film. That's why it's a thin film, because when you spray paint the atoms down, you spray paint a long time, you can make a thicker material. You spray paint a little, you make a thin material. You're never getting down to the atomic layer level. So it is still, considered a bulk semiconductor in that sense, but you have a thin film coating there. So there's a lot of technology. There's a lot of technology that needs high quality semiconductors. So they need the crystalline silicon, like the microprocessors. They're never going to work on amorphous silicon. The amorphous silicon is just not a good enough material for that. But for anything where you don't need it to be fast, but you want it to cover a large area, you want to be able to put it on any type of material you want to be able to bend it and move it and flex it or whatever, then amorphous silicon is for you.
Right. Yeah, so you have another paper here. So if I understand this correctly, Jim, it's a manufacturing process that it sounds to me that you can almost dial up the properties that you're looking for. And given the dimensionality, it can actually create it. So this another paper is about amorphous silicon in which you have germanium nanocrystals embedded.
In an amorphous silicon matrix. That's right. And that's a material that you can only make if you have two separate systems, one that makes the nanocrystal germanium and the other that makes the amorphous silicon, and you inject the nanocrystals from one into the amorphous film of the other. And they're exactly right. We found that as we changed how many germanium nanocrystals we had, we could change whether it was electrons carrying the current, or what's called holes, which act like electrons but have a positive charge carrying the current. These are good materials for these are materials that we looked at for applications called thermoelectrics. So a solar cell is called a photoelectric. It takes light, photo, and creates a voltage. Right. Thermoelectrics take a temperature difference, thermo, and create a voltage, electric. So anytime you have a temperature difference between a hot and cold, this material would generate a voltage for you. And there's a lot of applications, like there's a lot of heat that's wasted underneath the hood of your car. And could you take these devices and use them to create a voltage and, like, say, recharge the battery of your hybrid automobile? These materials exist. This phenomena is real. They exist. The issue is just to make them better and to make them cheaper so that they become cost effective. And so that's what people are like myself and other people are working on.
So it's just increasing the efficiency now, right? So
there it was looking at trying to see if we can improve efficiency, but we're also looking at it. So remember, I said there were two reasons to study this: science and technology. And I talked about the technology. The science is interesting because every theory we have for how silicon works starts with the phrase, assume a perfect crystal. And that's the reason we do that, and that every class we teach in solid state physics to our students, it deals with crystals. And that's because we have nearly a trillion atoms in a cubic inch of a solid. And we either have to solve Schrodinger's equation for a trillion atoms, or we have to be clever. And so one trick is if the atoms are arranged in a perfect crystalline arrangement, like a checkerboard, where there's a black square, white square, black square, white square, then that means with a checkerboard, I only have to figure out what a couple of squares are doing, and then I know exactly any distance within the board, whether I'll find a black square or a white square. You just tell me how many steps to the left, how many steps, up. If the squares are totally random, different sizes, different orientations, different this, different that, knowing what a few squares are doing doesn't tell you anything about what the material is at some other distance in. So you're kind of like, you're in deep trouble. So for a long time, people were ignoring amorphous materials, not because they were uninteresting, not because they were rare, but because they were hard. and physicists are one thing, they are lazy. So they say, ooh, that problem's too hard. What's on TV? So, and I'm telling you that crystals, when I say crystals are rare, I have an economic argument. Of the two forms of carbon, diamond and soot, which one is more expensive? Right? Obviously,
I would imagine
diamonds. Diamonds are expensive precisely because they're rare. If you went down and you came out of the subway and you had diamond dust off of your shoulders and everything, no, it wouldn't be a big deal. You would give a soot ring to your beloved as a sign of your affection. But I would not recommend. I made that mistake once, never again.
So I want to touch on something else, Jim. So you have a recent paper, I don't know if this is published or not, proton radiation-induced enhancement of the dark conductivity of composites.
Let me talk about that. That's a great paper. And that came out earlier this year. One of the few things to come out of 2020. We found that if you add just a small number of nanocrystals, the ability to conduct electricity of these materials increased dramatically. And this got the attention of one of my colleagues at the University of Minnesota, who works at CERN, the particle accelerator. He does particle physics. And they were going to upgrade and improve the intensity of the proton beams at CERN. And the problem is that the detectors they use to detect the creation of these high energy particles in these proton collisions, they use crystalline silicon because it's got a good conductivity. It's really good conductor of electricity. But the problem is that they suffer radiation damage. And so as you leave them in these proton beams, their properties would degrade. And eventually they would no longer be useful.
You're replacing them if you do it that way.
I'm sorry? Yes. And it's just like the scale, the size, the number that you would have, it just would not be realistic.
Right.
So amorphous silicon, though, every atom is in the wrong place. So it's what's called radiation hard. If you come in with a high energy proton and it knocks an atom and it moves it out of its position, the material says, "Oh, that's adorable. Like I care." It doesn't matter because the whole thing is random. So how can you make it more random? But the problem is it wasn't a good enough conductor of electricity. So since we found that putting a small number of nanocrystals could improve the properties of the material, would this material still be radiation hard? Does this improvement persist when you expose it to a high energy proton beam? So that was an experiment collaborating with my colleague Roger Rusak at Minnesota and Rachel Yohei at Florida State University. I sent my student down there with some samples, and they irradiated the samples. We thought that there might be some defects that are created that if we heat the sample up to a high temperature, which is called annealing, we could get rid of these defects. We came back, we brought the samples back, we did the measurements, much to our surprise. So we did not see metastable defect creation. We did not see no change. We saw an improvement in the ability of this material to conduct electricity. The resistance went down even further. If you heated up the sample, it didn't go away. It stayed. No matter how many times you heated the sample up to high temperatures, you couldn't remove this improvement. We had a sample, we took it out of the chamber, we came back 8 months later, we measured it, completely identical to what we measured before. So it's a permanent improvement.
What's the physics, Jim? Do we know? So I have two questions. The first one is, when you embed the nanocrystals into the matrix,
Yeah.
is there any pattern there? It's also random.
That goes in completely random.
Yeah.
What the improvement just due to the nanocrystals is due to the fact that at low concentrations, the nanocrystals are just donating extra electrons to the surrounding amorphous silicon. So it's making it so that there's more electrons to carry a current, which makes it easier to carry a current. And then if you put too many nanocrystals in, it turns out you get other defects that wipe this effect out. So we find like a sweet spot for how many nanocrystals give you this improvement. For the irradiation, then, why does it improve further?
Yeah.
That we don't know. In fact, we wrote a paper. We said, well, there's two things that could be due. It could be due to this or it could be due to that. So we tested this. It wasn't this. We tested that. It wasn't that. and so it's not just a cool effect. It's an I love a mystery cool effect. It's like, I mean, there's nothing that a physicist. So Enrico Fermi, one of those brilliant physicists of the 20th century, had a great line. He said, when your observation agrees with your expectation, you've made a measurement. When your observation disagrees with your expectation, you've made a discovery. Right? And you always go into an experiment expecting a certain result. Otherwise, you would never have done it. And most of the time, you get what you expect, and that's good. You make this measurement, and you go on and go on. So we've written this paper up. We published it because we had the results, even though we don't understand it yet. I just submitted off a grant proposal to the National Science Foundation. So if any reviewers are listening, remember this, where we would like to continue these studies. We want to try to understand. There's lots of things that we still, when I said this and that, I did just 2 tests. There's lots more tests. There's these, them, and those that we can test. And then we also want to say, hey, this was just like a few samples that we irradiated. And then, of course, unfortunately, COVID shut us down for many months. But could we improve the effect? Could we change it? Could we what there's so many different parameters that we can now vary and say, could we make it bigger? Is this as big as it gets, or can we make it, it improve the conductance of the material by 10 times, over 10 times? Could we make it 100 or 1,000? I don't know. We'll have to see. And then we make devices. Yeah.
Yeah. Is it practical enough now, Jim, that CERN could use it?
Not yet, but we're getting there. We want to see that we have an interesting observation. We have an interesting effect. And the next step is to build on this, understand it, optimize it, and then actually make a device and see. It's very possible that CERN could use it. It's also possible it might find applications in satellite-based solar cells that are exposed to cosmic rays that this might resist. And it might be useful just even for plain old vanilla devices here on Earth that you would like them to be a little bit better, a little bit faster in carrying current. So we don't know yet. But that's the fun. That's it. To find something and to say, wow, this is really cool, and I have no idea what I'm looking at. That's what you live for. That's what you live for.
Presumably, once you explain the physics, there might be more places you can go, right? It sounds like there is an optimization aspect to it because you found that sweet spot where it is most effective. So if underlying physics is understood, then perhaps there are more places you could go with it.
From your lips to the National Science Foundation's ears. Yes, that's exactly right. That's exactly right. It's but and that's the thing. You see something, and that you write a proposal. You try to continue the research. We're going to try to do this regardless. But it would be easier and better if we can pursue this, because it's a fascinating project. And this is also, I'm doing the research always with graduate students, always training them, because the way to teach someone to be a research scientist is to have them do scientific research. No one in human history has ever gotten a driver's license by just taking the written exam, right? You need some behind the wheel training. And so this is what actually a lot of the research that's being done, all over the country, all over the world. Most of it, and certainly the ones that are done at the universities, is really, you think of it as research, but it's teaching. It's teaching someone how to be a researcher by having them do research. And then those people go out and they work at industry, they work at national laboratories, they do other things. But they've learned how to do this. They've learned how to take experiments, take data, analyze it, how to figure things out. And then they go off and they work for Honeywell. They work for, other companies. They work for Medtronic and make biomedical devices. This is, this is our teaching that we're doing, and it's also just tremendous. It can be a lot of fun. It can be very frustrating, but sometimes fun.
Excellent, Jim. This has been great. Thanks so much for spending time with me.
Oh, it's been a pleasure. Thank you very much, Gil.
Thanks so much, Jim. Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.